Hi everyone, my name is Charlie Como, and this is my video lab report for the fourth lab. We were given a video of a mass oscillating on a rope and are asked to analyze its motion as a mass spring system. In order to do this, we'll use Newton's second law, the energy principle, and Hooke's law as our fundamental physics principles, and use the software's Tracker to extract our data, and Excel CSV to convert into a readable format, and VPython to create a computational model of its motion. And we are interested in these results because if we do it right, we can also model the motion of you right here the next time you go rip swinging. So here we have our free body diagram and our relevant energy formulas for the energy principle. The only forces acting on our object will be the gravitational force, which always points to the negative y direction, and the spring force, which will point either towards or away from its fixed position, depending on whether it is stretched or compressed. For energy, we will have kinetic energy, gravitational potential energy, and spring potential energy, whose quantities can be calculated by the formula shown. We will choose our system to be the mass, spring, and earth, which will make our surroundings nothing, which will make our energy changes internal to our system and yield a net energy change of 0, because all our energy is conserved within our system. Note, we can also model our rope as a spring because on a microscopic level, the rope's tension is due to the stretching bonds, which can be thought of spring-like forces. In addition, we'll use Newton's second law to calculate our object's new velocity and position iteratively, as we have done so in previous labs. So this is what it looks like when we extract our data in Tracker, and now we are ready to do a few more quick derivations to complete our initial conditions. To find the stiffness of our spring, we can use the formula for the oscillation time period of a spring. To find t, we can use Tracker to find the time between one crest and use that to solve for k, getting 7.02 newtons per meter. Note, I use the y direction data instead of the x direction because our spring is set up vertically, not horizontally. Now, to find the rest length of our spring, we can use the mass at static equilibrium to set up our net force equation like so. Because both forces at that time point in the y-axis, the spring force becomes equal to the negative of the gravitational force, and when we solve for L0, we get 0.139 meters. After that, we put our data into a CSV file, and this is what it looks like when we put all this together in GlowScript, with the left side being our initial conditions and our right side being our iterative calculations done in a loop. When we analyze our model's motion, you can see that they decently intertwine and step together. When we analyze for our energy principle, our model produces this graph. Note how the spring and gravitational potential energy visually offset each other, and when summed with the kinetic energy, becomes 0 in the orange line. This is exactly what our energy principle predicts from our previous equation, and our model satisfies that here. For the what does it mean questions, I created the two estimates of oscillation periods by calculating the average time the spring takes to go from crest to crest, as shown in Tracker for both the x and y directions. We can use this previous formula to calculate our spring constant and construct our models like so. Note how the y position data yields a much better fit, and that is because our spring is set up in the y direction instead of the x. Our x position data can be better modeled as a pendulum swing instead of a spring. So, in terms of errors, I noticed how my model overpredicted the motion at the crest and troughs. I think this was a combination of unaccounted dissipative forces like friction and air resistance, human error in data tracking, and the lack of more points at those times. So a couple ideas to improve for next time will be to re-record that video with a better camera so that a higher resolution can make the position of the mass more clearly, and more frames per second would yield more data points, and to put a bright colored dot in the center of the mass so that plotting its position in Tracker would be much easier and help reduce human error. And another interesting alternative model that we could analyze as a follow-up would be to pull the mass straight down from rest and analyze this motion only the y direction so that energy is not lost from swinging side to side. Overall, I thought the model did a pretty decent job and was pretty happy with it, and that is that. Thank you.